to begin with. So we've got Rayhan and Luke having fun on a uniform seesaw of mass 20 kilograms. Rayhan weighs 70 kilograms and is 10 meters from the pivot. Luke is 8 meters from the pivot and the seesaw remains horizontal. In other words, it's remaining in equilibrium. And we're going to try and determine the reaction force at the pivot of the seesaw, and we're going to determine Luke's mass. Now, we looked at this question with the other group yesterday, and this is a ridiculous seesaw because this seesaw is 18 meters long, which is like a giant, giant seesaw. It's also a really bizarre seesaw because the pivot isn't even in the middle. So you get it though, whatever. It's just a fake real life question, really. So where should I put the pivot? Which end is it closer to? If I'm going to have Rayhan on this end and Luke on this end. It's closer to Luke, isn't it? Because it says that the pivot is 8 meters away from Luke. So I'm going to put the pivot point there. And this distance is 8 meters. And we've also seen that Rayhan is 10 meters away from the pivot point. So what other things do I need to add on to this? So I've done some of the dimensions. What other things should be added? The forces, yeah. What's some of the forces, Hassan? 20 newtons going down. It's not going to be 20 newtons. It's going to be 20 G going down. And where would that be going down? 9 meters from one of the ends. So that's going to be a 20 G. Now, this is where people in the other class have been getting confused, and every year people get confused. You either can label this distance, or if you want, you can label this distance, or, there's all different kinds of distances you can label, but you don't want your diagram to become too busy, because when it becomes too busy, our brain can't extract the information very easily. So you need to be careful about what you put on that's useful for you, okay? What other things do I need to put on? Shahid? Okay, so Rayhan is 70 kilograms, so I'll do a 70 G. Luke, I don't know, so what should I call him? MG. Anything else? Yeah? Yeah. Because we are looking at, do you remember which thing I make you imagine that you are? You imagine that you're the beam, okay? The beam doesn't, when you're lying there balancing on the thing, you don't actually feel something pushing you up where your head is, do you? You would only feel a normal reaction if you were Rayhan on the end of the seesaw. You would feel your weight and you would feel your normal reaction pushing you upwards. So we're not imagining that we're Rayhan or Luke, we're imagining that we're the beam, so they don't have normal reactions there. The only place you feel something pushing you up is here. So I better change this to Rayhan and Luke so we don't think that Rayhan is referring to a normal reaction. But that's a very good question. No one's asked that yet, but it's because we're considering the beam as the thing we're concentrating on, not the other particles. Okay, so now we've got to this stage of the question. There's actually only two things you can do. What are the two things you can do in a moments question? Take moments and resolve up and down. That's literally the only two things you can do, right? Obviously, with taking moments, there's a lot of choices you can make because you can take moments from many different points. And we know if you take moments from any point, because it's in equilibrium, there'll be no resultant moment. So what do you think is the best way to start with this one if we're trying to find the normal reaction? Okay, if we resolve up and down, we will get R equals 70G plus 20G plus mg. So it's going to be useful, but I've kind of got a bit stuck because... So if I take moments about R, Luke, the R will disappear, and I can find out what your mass is, which is fine, but that's what part B of the question is. So at this stage, I'm just trying to train your minds to think, where would you take moments from to get the information as quickly as possible? What did you say, Shahid? Yeah, if you take moments about where Luke is, the mg is a zero distance from that point. So the mg is going to completely disappear. So you're going to imagine that this is where the pivot is for a second. And we're just going to think about the forces that are acting. Which are the two forces that are acting together in this rotation? Yeah, the Rayhan and the weight of the beam. Those are the ones that are going in that direction. The normal reaction is going in the other direction, so that's going to be on the other side of the equals sign. So we're going to have 70G multiplied by what? 18, because it's the distance from 70G all the way to Luke. And we're going to have 20G multiplied by what? 9, because it's the distance to the middle, okay? So it's 20G multiplied by 9, and that's going to be equal to the normal reaction multiplied by 8, which is 8R. Now, what you may be tempted to do, because I know some people are lazy and don't like to write lots, is they may be tempted to kind of put this all in their calculator as they go. But the examiner is looking for this. This is what the examiner is looking for, okay? So make it easy for them so that they give you the marks as freely and quickly as possible. They want to see force, distance, force, distance, force, distance, or distance, force, whatever. They just want to see those things. Then you can do the solving on the next line. It's like I've always said in mechanics, this is the most important part. The rest of it's just solving a baby equation, right? So we're going to find out what R is equal to. So we're going to do, I would leave G in here, okay? I wouldn't get rid of G. I would just leave G because it's fine to leave your answer in terms of G. So if we leave our answer in terms of G, we're going to have 70 times 18 divided by 8 plus, well, actually I'm just going to do it on my calculator because I'm going to confuse you if I write it in that kind of way. Anyone started working that out yet? What they think it is? 180G, thank you. And we're just happy to leave it in terms of G. So if you've got G in these questions, leave it in there as long as you possibly can. And then if you need to at the end, if they've asked for it specifically in newtons, then you can give it in newtons. But I'm quite happy to give it like this. Now we're trying to find out what the mass of Luke is. There's two different ways we could find the mass of Luke. What do we think is the most efficient way to find the mass of Luke? Ahmed? Yeah, you're going to use the thing that we've done up here, which was resolving the forces up and down. That's definitely going to be the most efficient way to find out what Luke's mass is. But what's another way that we could have found out Luke's mass? We've mentioned it already. Moments about? Yeah, you could take moments about R. If you wanted to, you could take moments about Rayhan, but you'd then have to also put this one in as well in case you've got that one wrong. But there's many, many places you could do this. So we're going to use this information up here. Now you can see why leaving it in terms of G is a good idea, because I get R, which is 180G, equals 70G plus 20G plus mg. And because of all the G's in there, it's really easy to see what we think m should be equal to. So we've got 180G, take away 70G, take away 20G. So that's 90G equals mg. So m equals 90. And I was saying to the other, there's no way Luke's 90 kilograms. So this is another ridiculous feature of this question. As well as there being an 18-meter seesaw, we've said that Luke is 90 kilograms. It's not even talking about you, Luke, so it's just someone random that popped up in this question. Okay? So when you really break these questions down, they are just drawing a careful diagram, resolving, and moments. That's it. If you ever try and find yourself doing something different, you've gone way off-piste, okay? You've gone way too far in the other direction. So I'm just going to do one more, and then you're going to be doing some exam ones. Can I go on to the next page, or are people still writing that down? Okay, your silence is telling me I'll go on to the next page. Okay, a uniform beam AM, AB of mass 40 kilograms and length 5 meters rests horizontally on supports at C and D, where AC equals DB equals 1. Now, I probably would pause there and I would say, okay, well, I'm actually going to just start drawing that part of the diagram. So when I draw that part of the diagram, they've told me that the beam is called AB, which means the ends of it are AB. What else have we got? Oh, it's a uniform beam, so I can immediately come in here and say that's going to be 40G. And the supports at C and D, so we're going to need to draw two triangles. Between A and C is 1 meter, so it looks like I'm going to have to put a support here, which is C, and that is 1 meter. And between B and D is also 1 meter. And the whole thing is 5 meters. So this just depends on what your kind of preference is of what things to label, because there's many, many different things you could label. I guess if the whole thing is 5, I probably would say, well, this one is 1.5, so that it's halfway along, which means that this one is also 1.5. And at this stage, I'm probably going to want to draw on some normal reactions, but I think I better read the rest of the question for a second, because there could be a bit more information. When a man of 80 kilograms stands on the beam at E, the magnitude of the reaction at D is twice the magnitude of the reaction at C. Find the distance AE. Okay, this is something that, if you understand it, you'll be like, how do people get confused? But last year, lots of people got confused of which one was bigger, the normal reaction at C or the normal reaction at D. Loads of people got that wording really confused. So which of those is bigger, the normal reaction at C or D? D, because it says it's twice the size of the normal reaction at C. So if I just say, this is my normal reaction at C, you don't have to make the arrow bigger, but just to emphasize the point here, the normal reaction at D is twice the size of the normal reaction at C. Now, if there was no man standing on this situation, what would you have said about the normal reactions if it was just how you could see it? Pardon? They're equal. Why would they be equal? Because it's completely symmetrical. So it would be bizarre if one of the normal reactions was different. So I just want you to think, it doesn't matter where you actually put it, but I just want you to think to try and understand the situation. Where would you make the man stand so that there was more of a reaction at D than C? And if you get it wrong, the maths will still work, but I just want to think about this before we do the question to try and predict where it might be. If he was standing on C, it would actually make the reaction at C quite big because the weight is acting very close to the pivot point. He's going to be standing somewhere closer to the side that is D, right? If you imagine, I need to get my meter ruler again. Would you hold your hands out and like symmetrical? Okay, so at the moment the normal reactions are equal to each other. If I put a weight down over here, this hand, I'm presuming, is feeling like it's having to push up more. So like the closer the weight is to the particular pivot point, that pivot point is more likely to be feeling more of the reaction, okay? So we think the man is going to stand somewhere over here. I don't actually mind. If you put it over here and you got it wrong, the maths would still work and you would still get everything absolutely correct. So I don't want you like worrying about where to put it. Someone in the other group yesterday was kind of staring at the question being like, I don't know where to put the man. And it doesn't matter where you put the man, it will just work. Okay, so we think that the prediction is going to be somewhere over here, ATG, and that's where E is going to be. But I almost find if I put the letter E, this diagram becomes like even busier. Okay. Now I think we've done the diagram, which is a good amount of time to spend on the diagram. This is the most important bit. We want to find the distance between A and E. So if I can squeeze this in, that distance that we're measuring along there is the distance from here to here. So the diagram's getting even busier. Right, what do we think is the best thing that we can do now to try and find the distance AE? What might we need to do to get to that end goal of finding the distance? Bearing in mind there's only two things you can do. Resolve. Yeah, why is resolving a better starting point than taking moments, Luke? Because you only have one variable. You've only got R, and then the rest are just the weights of things. So resolving up and down is definitely the best starting point that we're going to do. So in the upwards direction, we have R plus 2R, and in the downwards direction, we have 40G plus 80G. So 3R is 120. So R is 40G. So I'm going to go back to my diagram, and obviously when you're doing this on the whiteboards, it's easier because you can keep adding things to your diagrams. So I'm going to have 40G over here, and this one is 80G. Okay? Now we're trying to find out what the distance is, the distance between A and E. Where do you think, obviously we're taking moments because we've run out of resolving to do, so we've got to take moments. Just have a think to yourself, and I'm going to ask someone, I'm going to pick someone. Have a think to yourself, where would be the best place to take moments, and why would you pick that place? You could do it anywhere, but I just want you to try and think, where would the best place be? So I'll give you a bit of time to think, then I'm going to ask someone. Ahmed, where do you think you might take moments from? At D. If you took moments at D, okay, why would you choose to take moments at D?
Because you know how from A to C there's only 1 meter, so there will be the 1 meter there. So if you resolve, if you take moments at D, you can just.
So if you were taking moments from here, so you would need to have this distance, which is 3 multiplied by R. You've got this distance, which is 1.5 times 40. But this distance here is perhaps a little bit trickier to find out. It would still work though, but what is this distance here? No, it's not. This is where the distances are quite tricky to find. I'm going to see if we can figure out what this blue distance is. What's the distance from here to here? It took me 3 answers to hear the correct answer. I had 2.5, 3.5, and 4. So what is the distance of the blue one? If this whole thing is 4 and this is D, what's this one? That's 4 minus D. Now that's a really difficult thing to construct. Well, it's not a really difficult thing to construct, but under pressure, some of you came up and told me this whole distance was 2.5, then 3.5, then 4. So I'm not sure I'd trust you to do it that way, okay? But it would still work. You'd just multiply 4 minus D. Obviously, you'd bracket it when you multiply it. But I don't mind you taking it there. You'd still get the right answer. So Nahid, where do you think would be a better place to take moments?
But what if the man was on the other side of D, so it wouldn't be 4 minus 5?
It would all work out. The maths of it would all just completely work out.
You would do that at A.
I think A is the best place to take moments from. Why is A the best place to take moments from?
Because you just times ATG by D.
Yeah, because this is the distance that's the kind of annoying thing. We don't know what that is. So if I'm taking moments from here, the distance from here to here is just as simple as it possibly can be. So if they're asking you to find that distance, it's probably a good idea to take moments about A, because that's the distance of the force. Now, I'm pleased that Ahmed suggested that, because we've just seen you could work out all of the distances and it would completely work, but you're more likely to make a mistake when you're measuring the different parts of the beam. So you're much better to try and take it from a place that works as best as possible, okay? So we're going to try taking moments about A, because we think that will be as easy as possible. When we take moments about A, which are the two forces that are working together? Shahid, which two forces do you think are working together in terms of which two will go on one side and which two will go on the other side? The 40 and the 80, and then the R and the 2R will go on the other. So for the 40, we're going to have 40G multiplied by, what's the distance, Habib, from here to the 40G on the bottom? And then the 80G? And then the 80G is multiplied by D. And then for the other side, we've got 1 times R, which is 1 times 40G. And then we've got 4. Is that 4? Yeah. Now I'm getting confused. 4 multiplied by 80G. And we've got a nice equation to solve, because there is only one variable. The only variable that we have is the distance that we've got here. So if you want to, you could cancel G, which is why we like to leave G in as much as possible. So this is 40 times 2.5. That's 100 plus 80D equals 40 plus 320. So 80D is 260. So D is 260 divided by 80, which is 3.25. 3.25 meters, okay? Last thing I want to mention about this is 3.25 meters, is that closer to A or closer to B? Closer to B, right? Because the whole thing is 5 meters. And that's exactly where we predicted the man would be standing. We predicted that the man would be standing closer to D than to C. But imagine that you'd put the man over here and you'd said that this distance was D. Well, you'd still get, when you did your calculation, that D was 3.25. It just wouldn't be in the right place on the diagram. But the maths would still be completely identical, okay? So I'm going to get rid of that, otherwise that will make that bit of the diagram look a bit confusing. So what we're going to do is I would like you to try and get these first 2 exam questions done. I don't do anything from the textbook questions for this topic, because you need to see everything in these kind of worded sorts of situations right from the beginning. So we won't actually be doing anything from the textbook at all. So I'd like you to definitely get these first 2 done. If you want, there's obviously a few more of these as well. And then in a moment, about halfway through the lesson, we'll do hanging bars and rods, which is same thing, just as different situation. Okay, so I'll leave it up on this one, and let's grab the pens and we will get started, okay?